I'm currently principal software engineer at Martin Baker, where my team and I work on the software that's used in the ejection seats. I've also worked in a range of other different companies and domains over the past 15, 20 years. And I found that sort of breadth has given me quite a lot of oversight and insight into different aspects of software engineering in different organizations. And this is kind of good because I'm fascinated by the process of software engineering, and especially how you produce higher quality software with tighter time constraints and tighter cost constraints. So in this talk, we're going to talk a little bit about technical debt. I think pretty much everybody on the call is going to know what technical debt is, but we'll do a brief definition of it anyway. I've got 3 case studies that are from different points in my career, which I picked because they were aha moments for me as I've been learning. That led me to think about how I view technical debt when I work on a project. So there's a bit of a framework, if you like, for tackling technical debt. Then there's some anti-patterns, stuff that goes wrong consistently, stuff that really gets my goat. And of course, if you've got an anti-pattern, you kind of need some antidotes to help keep you sane. And then a little bit at the end, a reflection or some reflections on the future. What do I think? How do I think this could evolve in the future? I should say at the top of the talk that none of this relates to Martin Baker. This is all my own experiences from other organizations I've worked with. So, what is technical debt? Well, in short, it's the cost of taking shortcuts. So you take some shortcuts now, the net effect of that is that actually you have to do more rework in the future. It's not just about code quality as well. It can be because you forgot to update the build instructions for your application, or you forgot to set up your branches and permissions properly on your repository, or maybe you never quite got to the end of the verification. There's lots of different aspects to it, and there's some very good books out there. By way of a quick plug, can everybody see that okay?
Yes.
Yeah. So this I find an enormously valuable oversight guide to what happens with technical debt. They give a really good sort of set of classifications, worth a look if you're interested in the subject. Now, of course, it can occur for lots of reasons. The classic one is schedule pressure, but it's also about the skill of the engineers and the customers. And often it's just because the application has had a very long life and it's grown because it's been successful. And in many ways, that's really what you want. You want stuff that's going to run for years and that people are going to buy. So case studies. Like I said before, these case studies are things that have represented aha moments for me as I've been learning. And they all sort of tie together a little bit. I'll try and pull in the common threads as we go through, but I think they're quite interesting for many aspects. And what's cool is they represent the less sexy end of the spectrum. Most technical debt issues are related to, sorry, my battery's gone. Most technical debt issues are at the less sexy end of the spectrum. They're things like documentation, they're things like infrastructure, they're things you've forgotten about. So that's another reason why I find them quite fascinating. So first up, software that should never have been written. That's quite a strong statement. About 15 years ago, I worked for a small consulting company, and we did lots of different projects on lots of different platforms for lots of different customers. Now, this one was something we'd inherited. A company had purchased a custom accounting application, and the firm that they went to was the one that produced their website. The firm had no experience of this sort of application development, and as far as I understood it, the development of this pretty much bankrupted them. And we were then approached to go and finish it off. Ouch. I mean, there's no other way you can describe that. The thing was 25,000 lines of code, a mixture of SQL store procedures and VB. No installation scripts, no test scripts, no CI server, no bug list beyond a spreadsheet. So no documented release process or change control process. And the customer thought it was nearly done. So you can probably guess where this is going. Now, the the year or so I worked on this, it was between 1 or 2 days a week of my time. So do the maths for a standard rate. It's a lot of money. So how do you get out of that situation? What do you do? Well, the starting point was to agree a process for identifying and prioritizing and fixing the defects. The crucial thing here was to build awareness and trust with the customer, and they needed a mechanism for controlling the work so that they could actually get to the end and feel, yes, we've got what we need. Now, they didn't have the money or the motivation to fix everything, and actually they didn't need to. They needed to do enough to add for the system to add value to the business and for it to be maintainable into the future. So here it was a relatively straightforward task, if somewhat depressing. I got to the point where I could predict defect costs to within 10% because the patterns were so repeated. Now, as we were going through, we wrote manual test scripts, and these provided both a verification mechanism that the customer could use, and they provided documentation about how to use the system. There wasn't enough money in the budget to actually automate everything, so this provided quite a nice hybrid approach. Scary thing, of course, is that these defects that the customers were seeing were like icebergs. So every defect the customer raised, I'd expect to find 2 or 3 myself once I started debugging that area of the application. So what were the problems? Well, first, fundamentally, the customer thought they needed a custom system. The supplier thought they knew how to build it, but they only got part way through. And I joke about this to my friends and colleagues, but my first rule of custom software is don't. It's easy to get wrong, and if you do, it's going to be very, very expensive. Now, next step, or next example. This one's a totally different ballpark. So this is a library upgrade, a compiler upgrade on a large successful product. So large in this context is sort of 5 to 7 million lines of C++ and C#. Visual Studio solution was something like 90 projects all told. And if you knew what you were doing with a fast developer machine, you could get the build down to about 20 minutes or so. The application was developed by multiple teams in different tech centers on different continents. So here you've got a mature, successful product in developed by a big company with engineering teams that know what they're doing and engineering managers that know what they're doing. So I was part of a team that worked on the compiler upgrade for this, and we were responsible for doing second and third party libraries that were consumed by the application. Now, the expectation was that it would take 5 to 6 weeks, and it took closer to 4 months. So remember, we've got an experienced team here. As a team, we knew what the scope was because we knew what the libraries were. And as we started the project, we defined the workflow that would guide our work. So something like download the latest source code for the library, check the licensing changes, check the functional changes, rebuild for whichever platforms were required, verify it works as required within the product. Then you'd review it, and then you'd integrate your changes onto the main line. Now, there are a couple of gotchas here, because so far it all sounds straightforward. We found that the previous maintainers had not bothered to document their configuration options, so the compiler settings for each library. So that meant we had to do everything from scratch. Now, this is a totally different ballgame. So the to-do list got a lot bigger. If you're dealing with third-party libraries on a product that you're not completely familiar with, you're going to have to understand how the library's behavior is controlled by the various build options, and you need to understand which bits of the library are being consumed by your application. So if you have to do this from scratch for everything, it's going to take you a long time. And bear in mind, our customers, the people consuming these libraries in different bits of the application, were on multiple continents. So it's not like you could walk across to your mate in the next office and ask him. There was a good chance you'd have to contact somebody in the States or in Japan or in China, and it'd be a couple of days before you get an answer back. So the learning cycle was a lot longer. So our approach as a team changed. We had to do much more upfront investigation to figure out what to do. And we had to make damn sure that we got the documentation right this time. Crucially, senior management was supportive. They got it, they understood it, and they accepted that we had to do this. but actually it doesn't make it any easier in some ways. You still have to tough it out. And we ended up with quite a good sense of gallows humor as a team as we worked our way through to the end of the project. Now, I'm a big fan of metrics. So I was collecting quite detailed data on this from the libraries I was responsible for. So these are my task outs from the work. So this is the work I was doing on libraries that I'd been assigned to upgrade. So excluding things like reviewing my colleagues' upgrade activity as well. So more than half of the time was spent on rework from previous projects. In other words, when the libraries hadn't been properly built in the first place. So our technical debt doubled the cost of the work. That's a scary number. You know, we doubled it, or the technical debt doubled it. Now, the senior management response to this was actually very positive. You know, we didn't get shot. It wasn't the team's fault that the world was in this state. They recognized that the work we'd done was valuable because we'd actually put in place a reproducible upgrade program for next time. And they also recognized that the approach in the future for the next compiler upgrade needed to be different. Now, this sort of ratio, where you get a doubling of a project's cost due to technical debt that gets discovered, I've seen it on other projects I've worked on over the years. It's far from unusual. The thing is, unless you track these metrics yourself and try and get the handle on them, you're just going to think, oh, that took a long time, I wonder why. Now, as an aside to this, the technical debt was much harder to estimate accurately. So if you're using PSP techniques and you understand the technology stack, you can get to within 15–20% without too much difficulty. This stuff was way noisier in terms of the distribution of the estimation errors I got. So that feeds straight through into your cost estimates being less predictable, and crucially, your schedule estimates being less predictable. You're going to find lots of discovered tasks, and you expect it to be harder to predict when you're actually going to finish the work. But actually, at the end of the day, the team did a good job, and it was recognized for doing a good job. So overall, you know, the experience was positive. So what did I take away from that? Well, clearly the lesson's split into sort of two parts, if you like. During the early phases of this product's development, sort of, I guess this would have been around the late 90s, 2000s now, give or take, there hadn't really been enough work done to manage the libraries, the third-party libraries that are being used. Libraries are great if you want to get functionality in quickly, but they impose an ongoing cost. And the problem is, unless you address that at the start, it's going to bite you later on down the line. And the thing is, it's not sexy or fun. Nobody really wants to do this. So it's always something that you can push to the back of your mind and forget about until 10 years later, you realize the compiler's no longer available, the vendor's gone out of business, or whatever else it is. So that's the stuff that happened in the past. As to the work prior to commencing the upgrade, with hindsight, the senior managers recognized they hadn't spent enough time actually doing upfront elaboration and digging through to find out what state the guts were in. They kind of quoted for doing the plumbing without taking up the floorboards and inspecting the house first. We knew what the libraries were, so you know, it's perfectly possible that with a bit of effort we could have actually sampled a few of them, picked maybe the most important items, the most valuable items, done a bit of digging to try and figure out, well, how bad is it really? And that would have enabled us to at least get a fighting chance of realistic estimates, or just identify that we had lots of technical debt. So my last example is onboarding a small desktop application. Now, this will be familiar to anybody who's had to maintain an in-house written custom application. And I said onboarding deliberately. The example in question was actually a small desktop utility that was widely used through the company. It had been originally written as a personal development project by an engineer who wasn't a software engineer, but was perfectly smart and capable. The release process for this was that you would build it on your developer machine, you give it to a colleague to test, and then you copy the resulting installer into a folder somewhere on the network. And And the thing that I like about this was that the individual that developed this application later went on to work in DevOps. There's a certain irony about that I like. So the solution here was actually pretty straightforward. It was planned rewrite. We knew we were going to do some work on it anyway, so actually fixing the internals to be buildable and testable was not that big a deal in the grand scheme of things. Adding automation in terms of the test suite, again, was reasonably straightforward. So that meant that anybody that was working on it in the future would be able to start from a clean build and a clean test suite. So what was the learning from that? Well, it was actually a couple of things that made me sit up and take notice in this one. The first thing is that there's a world of difference between somebody who can build an application and an individual or a team that can actually manage the whole life cycle. Now, it's easy to think if you can code, you're a software engineer, but actually there's much more to it than that. And it's not just that the software engineers are being precious about their job titles. I've seen this issue on multiple occasions, again, where individuals with some domain expertise have developed an application functionally, but have not had the skill to make it maintainable and therefore valuable for the longer term. Interestingly, it was one of the contributing factors in the previous case study because the application had grown very quickly by integrating applications and components from other companies with a strong academic background. So they could do the maths, they could build the applications, but they didn't necessarily have all the bits of the jigsaw to manage it through its life cycle. And it was on this project that I found myself thinking much more about the sequence of steps I went through to make stuff more robust. So, okay, I can build it on a developer machine, fine. Can I build it on a CI server? Well, in this case, I couldn't because the architecture of the application was a problem. Could I run a test suite on a developer machine? Well, no, there wasn't one. It was just a Word doc with some screenshots. Could I write a test suite? Well, no, not as it stood, because the architecture of the application, the same reason you couldn't build it on a CI server, you couldn't write tests for it very easily. And that was the thing that drove the need to re-architect the application. So I started to think about a structured way of tackling technical debt and how I thought about it when I came onto a project. And it also made me think, well, actually, you know what? It's the boring stuff that gets you the most value. High maturity processes, things like PSP and TSP, automation everywhere, just makes your life a lot easier. And if you've got those in place, actually, a lot of the drudge stuff goes away. And it doesn't have to relate to lots of paper or lots of admin overhead, things like that. It's actually surprisingly lightweight if you get it right. So those were the sort of the three case studies. I've titled this rather grandly framework, but it's really how I approach problems with technical debt. Most of the time I've had to deal with technical debt is when I've actually been working on a project where the priority was something else. So in other words, it's been discovered work during the life of the project. So it's the sort of thing that's sitting there, like I said, an iceberg that's waiting to be discovered by the unfortunate engineer as they start out on their assignment. So when I'm thinking about this, I have a series of questions that I ask, and it's really split into two areas. So first up, looking outside of yourself, looking outside into the organization. What's the software? Where is it? Is it in source control? How do I know what's in the latest release? How do I know what's going to happen if it goes wrong? And how do I know what it's supposed to do? All of these things you can answer by going out into the organization and asking lots of people awkward questions. That's the hard bit in many ways. Looking inside of the product, okay, what about the build process? I'm going to try and get to grips with the kit. Can I build it on my PC? Can I debug it and test it on my PC? Can I build it on a CI server? That sort of series of questions about maturing the tool chain. As you go down the right-hand side of those points, the further you get down that at the start, the easier your life is going to be. Now, the interesting thing is that as you answer these questions, it will tell you a lot about not only the software, but also the environment that produced it and the values and the capabilities of your customer. So you're getting a lot of context that will help you understand how you can get the software over the finish line, if you like. So reinforcing that, the context stuff I think is the most important part. It defines the boundaries of what's acceptable or desirable, and it will have a big impact on what you can actually do to solve the problem. So I guess this is reinforcing it yet again, but understanding where you are is critical. That's not just about the technology, that's also about your organization. What do I need to do to get the technology into an acceptable state? What does the organization want me to do? And how do I reconcile these? There's a good chance they're not going to line up. Now, at the end of the day, if your customer trusts you and they think you are working in their best interest, then you do have a fighting chance, but it's never going to be easy. Fine, you've understood the problem. Now you've got to take action. Crucially, the customer needs to drive it. Nobody, if you're a customer, will care about the internal quality of the application. By and large, they don't care about technical debt. So they need to be able to control the work and they need to see the value of it. So if you have a well-maintained engineering backlog together with clear communication about the benefits of any changes, then you've got a fighting chance of prioritizing stuff. And there's no one rule for tackling this stuff. Sometimes you'll do incremental improvements as you go and nobody will notice. Other times you'll need a bigger planned refactor. But if you get it right, both you and your customer will see the benefits. So that was sort of the questions I ask when I'm thinking about projects with technical debt on them. What are the common anti-patterns that you see? Well, I kind of ended up grouping them into three separate categories. So sort of skills, stuff related to processes, and stuff related to automation. Now, I think I've said this before on this call, but most of these things are going to be related to human factors, not technical factors. And the technical factors aren't the sexy ones. You know, after all, who wants to spend the time sorting out an aging build system? So these three elements of skill often occur together. When I talk about unconscious incompetence, I'm talking about not knowing that you don't know how to write reliable code. I'm talking about not knowing that you don't know about the domain you're working in. Now, if you don't understand the technology you're working with, you're not going to be able to put together a good design. And if you can't put together a good design, you're going to find it very hard to write a credible plan because you won't know what you've got to do to build the thing you're trying to build. In that sort of scenario, you can often end up coding a series of prototypes until you've got something that sort of works. Now, if you don't understand the domain properly, even if you understand the technology, it'll take you longer to produce an acceptable solution. And if you don't understand either of them, then you're well and truly stuffed. Now, the metrics around this were quantified by Barry Boehm in his work on Kokomo 2. And if you've not seen it as well, Steve McConnell's work on the cone of uncertainty, which is very well described in that, my kind of go-to book for all things estimation. It's worth bearing in mind as well that Fred Brooks in 1975 observed in the Mythical Man Month that more software projects have gone awry for lack of calendar time than for all other causes combined. So what about process management? Well, processes provide a way of encoding knowledge to allow you to focus on the novel stuff in any given situation. Good processes reduce the information load you need to deal with on a day-to-day basis, and excellent processes make it much easier to do the right thing without even thinking about it. A side effect of good processes as well is that they're information radiators, so they shout about how well they're doing. And it's not for nothing do SPC practitioners talk about the voice of the process. Now, manually driven processes are where you don't have effective tool support. A lot of stuff gets run on spreadsheets, PowerPoints, Word docs, email chains, and so on. And these increase the cost of using the process, so detract from the value and effectiveness of the business. Now, a consequence of using manually driven processes is they don't radiate information. You get little or no data off them without putting in substantial work. So any metrics you have are likely to be less valuable. You won't be able to use them to make such effective, timely decisions. Now, a close relative of manually driven processes is where you have separate systems for different functions. So you'll probably have one bug tracker, you might well have a separate source control system, another project planning tool, and so on. Now, each tool will contain a model of your product and they'll contain some automation probably. So think about the defect resolution workflow and a bug tracker. Now, in that case, if you want an end-to-end view of what's going on, you'll need to spend quite a bit of time messing about with spreadsheets and reports to try and pull out bits of data and metrics you need and figure out how they all fit together. Net effect of all of this is that you'll get little or you'll get less measurement. And if you're not careful, you end up with metrics you can't trust. So the decisions are likely to be not as effective. So my third anti-pattern is around automation, or rather bad automation. Good automation is incredibly valuable. It eliminates variability and it drives design decisions in a direction that will provide more value to the business. So think about, for example, the last case study where we couldn't test it because of the underlying architecture. Now, good process, like a good process, an automation system allows you to focus on stuff that matters rather than trying to remember whether you actually did copy your installer into the correct folder. And of course, because it's automatic, you can capture and analyze more process data. It's much more straightforward. You've got instrumentation built in almost. But we're talking about anti-patterns here. Unreliable automation is a pain. If you're dealing with a legacy application that you're responsible for maintaining, hopefully it'll be a temporary state, and you should certainly be striving for that to be the case. Now, in the same bucket as unreliable automation is fragile automation. So this is the sort of thing where you have monster build scripts that are too fragile to update quickly and safely. They just grow and grow and grow and become a bigger source of the problem. Or maybe you just don't dare update them at all. My least favorite pattern, well, my least favorite anti-pattern here is semi-automation. Now, by that, I mean situations where some steps of the process are automated, but it's interspersed with manual steps. So you run a script to generate some code, then you manually modify the generated code, then you run the next step in the process. Now, I can think of an example like this where an upgrade to a third-party tool resulted in the code gen step producing source code that couldn't be compiled. The developer in this case just used the previous version of the generated file in the place of the one that wouldn't compile, and they didn't document that they were doing this. I kid you not. Actually, getting to the bottom of that took several weeks. It turned out that there was an undocumented change to the third-party application that we'd bought, and we'd not picked it up when the code gen step started failing. So what? Well, any one of these will slow you down, and crucially, they'll reduce your ability to learn. Obviously, if you have all of them, you're in a lot of trouble. But if you want to improve your organization's performance, you need to address all three because they feed off each other. So if you've got competent teams, you can start and you can execute projects with a realistic assessment of your risks. If you have decent processes, stuff is done in a repeatable, measurable way. And if you have automation, the drudge work is eliminated and you've got rid of a lot of variability. You can trust your builds, you can trust your tests. Now, we need feedback to improve. And that's the same is true of whether you're an individual or whether you're a team. If you want to get better, you need to practice or at least listen and engage with what you're doing. You need to listen to yourself, your team, people you admire, and figure out what the high performers are actually doing. You need an idea of what perfection looks like, or at least what good enough looks like. And then you can start to try different things in what you do in order to improve. The key thing about all of these anti-patterns is that they get in the way of the learning process. So you're going to be spending more time just fighting the system, fighting the technical debt, than you are actually thinking, well, how do I change what I do to add more value to the organization? Antidotes. If only it was that simple. At one level, part of me wants to say, well, the antidote is don't do dumb stuff, but of course it's never that simple. I guess these slides are really more about how I stay sane, or at least try to. There isn't a silver bullet. I don't have one. And what follows sounds a little bit like motherhood and apple pie, but please bear with me. I think the starting point is to understand yourself. If you want an easy life, then turn off your brain and fit in with the organization's norms. At some level, if you try to do this sort of stuff, you're going to need to swim against the tide. You're going to have to You're going to have to be able to tolerate some discomfort and stress, and you're going to need to persist. You also need to balance confidence and humility. A lot of the time you're going to be wrong. And in most jobs I've had, I've spent a significant amount of time disagreeing with my boss. So know your own mind. What really matters? What about setting a direction? Well, when you work in an organization, there's a lot of things outside your control. The project constraints, the structures of the organization, the customer's needs, all these things. It doesn't stop you finding areas for maneuver, something where you can try to make a difference beyond the original brief. Now, a lot of the time that seems to involve using the midnight to 3 AM slot to do the work, but actually it can be worth it, and it can provide the seeds for stuff that will actually be picked up and used by other people. You're not going to be able to fix everything, so you need to know what to ignore. There's only so many hours in the day. Now, that doesn't mean you ignore or sweep stuff under the carpet, because identifying and escalating risks is a critical part of engineers' job. But once you've raised a concern, if the company chooses to ignore that or do something different, then fine, you've made your point. You need to know when to stop. What about your team? Well, software engineering, I think, is actually a really social business. Most systems are too big for one person to conceive of and execute. So in spite of your enthusiasm for doing things better at some level, you'll need to take your colleagues and your team with you if you want process improvement to be anything other than an academic exercise. Your colleagues may not welcome your enthusiasm for this. For one thing, if they believe that any data being captured is going to be used as part of performance appraisal, they'll game the system. But hopefully you can persuade them that it's an endeavor worth pursuing. Now, with time, you'll learn as a group. Good ideas start as a minority of one, but it takes teams to change things. To quote Margaret Mead, never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has. As you progress, the team will talk more about what they notice in their day-to-day work, what they see in the project and the organization, and what they can do about it. So it's no longer completely reliant on you. You also need to remember that people have families, lives outside work. Every software engineering manager wants super motivated elite performers, you know, an old head on young shoulders. But what you've got is probably average, and that's okay. You just need to remember to plan for average and then know when to push yourself and your team for more. As you go out beyond your team, to your boss or your boss's boss, it's more about the big picture themes. Here's what we're trying, here's what we learned, here's what we're planning on doing next. Socializing the process is about communicating this and, crucially, listening to what other people, other groups have to say. There's a good chance they may be thinking about the same sorts of issues, and you can help each other. My last antidote is about the future. I think trying to make the future better than the past is a good antidote to despair. Now, I still find learning new technology stacks interesting, and I think I'm due for a new one sometime soon. But there are also others that are more important. There are also other areas that are important. Can you find a little bit of infrastructure in your immediate environment that you could do some improvements on? Most bug trackers and source control systems have the machinery to handle plugins and extensions. Does a plugin exist that will help you? Can you write one that will take some drudgery out of your day? And can you persuade your boss that a particular training course is a good idea? You won't know until you try. That's it for the substantive content, but I thought I ought to finish with a little bit of crystal ball gazing. Another Fred Brooks quote, "There is no silver bullet." But I think the thing that I've been struck by whilst writing this is that the problem's going to get worse in the future. So more people can code, and that's great, that's brilliant. Barriers to entry are lower. App marketplaces make it easy to sell your work. Cloud providers reduce the overhead to managing your own infrastructure. So more people are going to be producing more apps that need maintaining in the future. And a lot of these people are going to be learning in isolation and may not necessarily have a team to work with. So ubiquitous automation, things like GitLab, goes a long way to actually getting you started on this. You know, having your bug tracker, your build system, your test system, your source control, your release process, your deploy process in one environment just makes life easier. Things like Squale, I don't know if anybody's come across this. It's an automatic, it's a framework for analyzing code, but they have techniques for automatically quantifying technical debt, but only in the code base itself. Things like that will reduce the cost of profiling an application when you're starting to work on it. You'll never have one big system to cover all your needs, and infrastructure components will need to be changed over the years as products and services evolve. And sort of looking back to one of the earlier points about automation and connecting processes together, we'll always require components from multiple vendors. So plug and play integration is going to become much more important, so we can actually get data out of systems and learn much more quickly. So to close, Fred Brooks said there's no silver bullet, but there's lots of ways in which we can make things better.